So chapter 11 in our Jesperson text, Intermolecular Attractions and the Properties of Liquids and Solids. Intermolecular forces are what's going to hold everything together. So it's what separates gases from solids and liquids. So for gases, we know that they will expand to fill their container. Liquids will retain their volume but not their shape. Solids retain volume and shape. Right? So we can see a picture's worth 1,000 words here. Gases all over the place. Liquids, they fill the bottom of the container, but then retain the volume itself, but fill the shape of the container. And then solids, of course, we can see a rigid, fixed cube there in space. All right. Physical state of the molecule is going to depend on the kinetic energy of the particles. And if we go back and remember that the kinetic energy is proportionate to the temperature, right, the average temperature. So intermolecular forces then, energy of interparticle attraction. Okay, so what we're looking at here is how two different particles are attracted to one another. And that's what's going to help determine that energy. Physical properties of gases, liquids, and solids are going to be determined by how tight those molecules are packed together and the strength of the attractions between the molecules. Okay, so physical properties of gases, liquids, and solids, it boils down to how tightly the molecules are going to be packed together. In other words, if it's a gas and we put pressure on it, we're forcing those particles near each other. And then the strength of the interactions between those two particles. So intermolecular attractions then, converting a gas, you can go to liquid or solid. The molecules have to get closer and closer together. So we're going to either cool it or compress it. Those are going to be our two options. Converting a liquid or solid to a gas, we're going to require the molecules to move further apart. That means we're either going to have heat or reduce the pressure, i.e. expand, increase the volume. As temperature decreases, kinetic energy of molecules will also decrease, which means they slow down and their attractive forces become more adamant to each other. At a certain temperature, molecules don't have enough energy to break away from the other molecules' attractions, and then they end up intermingling together and then becoming bigger, like a bigger component, and then a bigger component, until finally it's a solid. All right, now inter versus intra. Now intramolecular forces is what we studied for a couple chapters there. Covalent bonds within the molecule. Obviously they're strong because they form a molecule. The delta H for a bond in HCl, for instance, is 431 kilojoules per mole. Now there's also going to be intermolecular forces. Now this is again the forces between two different molecules. The attraction forces between the molecules is typically going to be weak. And in the same compound, HCl, that's been vaporized, it's 16 kilojoules per mole. Okay, so in other words, what we're saying is the covalent bond between the two is very strong. Then we have that partial plus, partial minus interaction, and that's going to be a little bit weaker of an interaction. Still there, but weak compared to the bond itself. All right, quick review of electronegativity. Remember, it's the measure of attractive force that one atom in a covalent bond has for electrons of the bond, right? So we could form what we would call bond dipoles. Two atoms with different electronegativity values share electrons unequally. That means the electron density is uneven, and we have a higher charge concentration around more electronegative atom. In other words, the partial positive, partial negative that I just showed with the HCl. We'll indicate that with the delta notation, and it indicates a partial charge has arisen. Again, that should all be review. Now, net dipoles, remember we looked at symmetrical molecules. Even if they have polar bonds, can be nonpolar because the dipoles will cancel each other out. Things like CO2, we saw that cancel out. Oxygen pulled left and the other oxygen pulled right equally, therefore they cancel each other out. Now, if we have an asymmetric molecule, these will end up being polar because the dipoles are not canceling each other out. These molecules have a permanent dipole, right? And that's a net dipole. So molecular dipoles then can cause molecules to interact. The stronger that dipole is, the stronger the interaction will be between individual molecules. Decreasing the distance between the molecules will increase the amount of interaction. So hopefully that's pretty straightforward. When substances melt or boil, their intermolecular forces have to be broken. Okay, not the covalent bonds. In other words, we can't boil the hydrogen out of water, but we can boil water out of water, right? And it makes steam. Responsible for the non-ideal behavior of gases, it's responsible for the existence of condensed states of matter. It's responsible for bulk properties of matter. In other words, boiling points and melting points. It reflects the strength of their intermolecular forces. Okay, so intermolecular forces are the interactions between individual atoms and molecules, not the bonds in the compounds. So when we melt or boil a substance, what we're doing is we're breaking the bonds between the two different molecules. So I have molecule A, molecule B, they're interacting, I give it some heat, and they move away from each other, and that's it, right? I cool it down, they get close together, and then they're attracted to each other. It's that simple. Now, there are three important types of intermolecular forces we need to be cognizant of. Dipole-dipole forces, i.e. hydrogen bonds, any kind of partial negative, partial positive interaction. Then there's London dispersion forces. And then there's ion-dipole forces, right? This is ion-induced dipole force. So a dipole-dipole attraction occur only between polar molecules. So in other words, we have to have that partial positive, partial negative interaction so that the positives and minuses can interact. Or the positives and minuses here, or the minuses and the positives, right? So we get an interaction between plus, minus, minus, right? So minus, plus, minus. The molecules need to be close together. The polar molecules tend to align their partial charges, again, positive to negative. As dipole moment increases, so shall this intermolecular force. So dipole-dipole attractions then, and you can see we have a cool little picture here of the molecules forming networks, right? So tumbling molecules. It's a mixture of attractive and repulsive dipole-dipole forces. So remember, if the two negatives get near each other or two positives get near each other, they're going to repel one another. So it's going to force them into an ordering. So attractions can be minus, plus, are maintained longer than the repulsions. Okay? So we'll get an overall net attraction. This is approximately 1 to 4% of the covalent bond. So again, it's not a strong interaction, but it's enough to make a difference in whether it's going to be a solid, liquid, or a gas. All right, so the interactions between the net dipoles and polar molecules, again, it's about 1 to 4% as strong as the covalent bond. And it's going to decrease with the distance. So the further these two molecules get away from each other, the less attractive forces are in that bond. So dipole-dipole forces increase with increasing polarity. So obviously, if we get a big enough moment, then that has a bigger attractive force, which means you're going to get a stronger bond in between the two, molecule A and molecule B. Now, a subset of the dipole is the hydrogen bond. So now this is a special type of dipole-dipole interaction, and it's a very strong dipole-dipole. In fact, it cranks up to about 10% of a covalent bond. Now, there's a key here though. Obviously it's a hydrogen bond, so it has to have hydrogen in it, and then it also has to interact with one of 3 other atoms. It has to be oxygen, nitrogen, or fluorine. In other words, it's an HF interaction, an HO interaction, or an HN interaction. These bonds are very polar, and that that loosens up that hydrogen to be attracted to another electronegative portion of the molecule. So electrons are drawn away from hydrogen so that we end up with a very high partial positive charge. Remember, it's a single proton. And so if its electron is being dragged away, then it's left with just a proton sitting out there. So hydrogen only has that one electron, so the positive piece of the hydrogen presents almost bare proton, right? So it's almost a proton all by itself. So element's small size means a high charge density. So the fact that it only has one proton and one electron is what's leading to this strengthening of this interaction. The positive end of one can get very close to the negative end of the other. In other words, If we look at water, the hydrogen bond in water, remember there's two lone pairs here on the oxygens. And you'll notice that's going to be the key. Nitrogen, lone pair. Fluorine, 3 lone pairs. Okay, so we're going to get that highly electronegative partial negative end attracted to that single proton positive end. And so all these interactions are going to show that. Okay, so hydrogen bonding in water then. So here we get a multiple effect, right? So we have the first water right here in the middle, and we've got an interaction with one other water here, and then one other water there. And then of course there's 2 other waters that are going to interact with the lone pairs on that oxygen atom. And so we end up forming a tetrahedral of just hydrogen bonding, okay? So it's responsible for the expansion of water as it freezes. So as water starts to freeze, it wants to get into this actually called this tetrahedral state. Hydrogen bonding produces strong attractions in liquids, and of course hydrogen bonding, the dotted lines here between water molecules and ice, form that tetrahedral configuration. Okay, so that's all of our dipole-dipole interactions. Now the next one on our list was London forces. London forces, whenever atoms near one another, their valence electrons will interact. Repulsion causes electron clouds in each to distort and polarize. So that's a little weird to think about. Okay, so in other words, we have two compounds coming near each other, and the electrons on this one and the electrons on this one force each other to distort, exposing a positive side. So it's almost like you're creating a dipole. This instantaneous dipole results from the distortion. Now the effect is enhanced with increased volume of electron cloud size. So if I have more atoms, I have a bigger cloud. I have a bigger cloud, I'll see a more distortion, which means more dipole, instantaneous dipole interaction. Now the effect is diminished by increased distance between particles and compact arrangements of atoms. So if it's a really compact molecule, then it doesn't feel that. So in other words, a small molecule. If there's a huge distance between them, then you don't have any of this interaction as well. Now, London forces then are this instantaneous dipole-induced dipole attraction. We also refer to them as dispersion forces. Now, they operate between all molecules. So it doesn't matter if it's a neutral or a net charged molecule. It doesn't matter if it's polar or nonpolar. Any 2 molecules that come near each other will experience these London forces, these dispersion forces. Okay? The ease with which the dipole moments can be induced, and thus London forces, depend on 1. Polarizability of the electron cloud, points of attraction, which means number of atoms, the molecular shape, okay? And so that's, it doesn't matter like what 2 compounds are there, right? So it's how easily can you polarize the electron cloud, and then how big is it and what's the molecular shape. All right, so which of the following is the weakest of all intermolecular forces? Hydrogen bonds, London dispersion, dipole-dipole, ion-dipole, or ion-ion. Now, we haven't really talked about ion-dipole or ion-ion, but I think it's pretty easy to see. Dipole-dipole would be weaker than ion-dipole, right? So we have a dipole as a partial charge, ions are full-blown charges. So if I have an ion, that's a +1, and then I have a dipole that has a negative end like water, and that would be our ion-dipole interaction. Ion-ion would straight up be 2 opposite charges. Okay, so that's going to be much stronger than dipole-dipole or ion-dipole. So which of the following are the weakest then? Well, it would be those London dispersion forces we just talked about. All right. So what is polarizability? There we go. It's the ease with which the electron cloud can be distorted. So large molecules often are going to be more polarizable, right, because they have a large number of less tightly held electrons. The magnitude of resulting partial charge then is larger and has a larger electron cloud. So if I have a larger electron cloud, you can think of it as being a bigger balloon. And so I can push the balloon a little bit easier when it's a larger balloon. If it's a small, dense balloon, not as easy to push, a little more rigid. But if it's a big expanded balloon, it's easier to push on. It's like a big old pillow, right? And the more you can push on it, the more you can distort it, the more polarizable it's going to be. So boiling points of halogens and noble gases. So you can see here, the bigger they get, the boiling point, right, is going up. Let's see. Here we have helium going down to radon. You can see again an increase in the boiling point. So just the larger they get, the stronger the London forces, and thus the higher boiling points will be. So the fact that I2, right, it's a bigger electron cloud, it means it's a bigger pillow, it's easier to polarize it, which means as the two big I2s pass each other, they'll polarize a bit, they'll form that instantaneous dipole that gives them strength between each other, and then we'll see an increase in the boiling point. Now, the second thing we said was the number of atoms, right? So here, you can see the chemical formulas themselves. We have 5 atoms, right? Here's 8, then 11, then 14, and we can see the boiling point here is going up. And as we go up even larger, the boiling point goes up even higher, okay? So again, it depends on the number of atoms in the molecule. So the boiling point of hydrocarbons demonstrates this trend, okay? Now, how intermolecular forces determine physical properties. So here's hexane versus propane. Now hexane, it's a really long chain, 6 carbons in a row. Propane, only 3 carbons in a row. The sites that are marked with the stars along this chain where attraction to other molecules can occur, right? So this is where we have electron clouds that can be pushed and pulled and distorted. And so the more sites we have, the more likely we are to have intermolecular forces start to play a part, have those dispersion forces. So hexane then, we see an increase in the boiling point by 100 degrees. All right, so molecular shape can also play a role. Increased surface area available for contact, increased London's dispersion forces. So, in other words, if we have a compound that is a chain, straight chain propane, pentane, excuse me, straight chain pentane, versus a neopentane. So neopentane, it's a little harder to tell what's going on here. Basically, neopentane has the carbons making sort of a cross. And then, of course, you have CH3, so you have some hydrogens here, right, versus a straight chain. So what we're saying here is that because you have less space for the neopentane to interact with another neopentane, we see a decrease in that boiling point. Not by a lot, but enough to make a difference, where you can see that it's going to be the fact that you have a long chain, it's easier for this to interact. All right, list all intermolecular forces for CH3, CH2, OH. Our options are hydrogen bonds, dipole-dipole attractions, London dispersion forces. All right, so we know our answer has to have London dispersion forces because we said every molecule has that. So it can't be just A, it can't be just C. All right, let's see. Can we have a dipole-dipole interaction? Well, to have a dipole interaction, we have to have a positive end and a negative end. And we have that here, right? So oxygen will be partially negative, hydrogen would be partially positive, and so we have dipole-dipole. All right, so that means D is out. Last but not least, is that dipole going to be able to give us a hydrogen bond? Remember, that's a dipole interaction that's exclusively hydrogen with either oxygen, nitrogen, or fluorine. We do have the oxygen, and therefore our answer would be B, hydrogen bonds, dipole-dipole attraction, which is the hydrogen bond, and then London dispersion forces. All right, in the liquid state, which species has the strongest intermolecular forces? CH4, Cl2, O2, or HF? This is in the liquid state. Well, right away we can see HF is going to have hydrogen bonding. So that means that should be our quick and easy answer. They gave us green this time instead of red. All right, what is the strongest type of intermolecular force in CHCl3? Ion-dipole, dipole-dipole, dispersion, hydrogen bonding, none of the above. Well, we know it's not going to be hydrogen bonding, right, because we don't have nitrogen, oxygen, or fluorine. So it could be dispersion because every molecule has to have dispersion. We're not forming an ion, so it can't be ion-dipole. Do we have dipole? So remember, carbon is a tetrahedral. Best I can do it drawing 3D here on a 2D dimensional whiteboard. So remember, the chlorines are all going to be pulling that electronegativity if we go look up our values. Hydrogen's going to be actually pushing. And so yeah, we do have a dipole. So that means our strongest then would probably be that dipole-dipole interaction. Which of the following has dispersion forces as its strongest intermolecular force? CH4, CO2, or O2? Or all of the above, right? All right, so we still have to talk about our ion-dipole attractions as well as ion-ion. We'll save those for segment 2, so we're at about 21 minutes here. We'll call this one a wrap. And so we'll pick up next with ion-dipole attractions. Stay tuned.